This week's problem is, given a linked list, remove the nth node from the end of the list and return its head. Let's make sure we're on the same page for indices. We'll be using the Python way of indexing. So the first node is at index 0, the second node is at index 1, and so on. For the reverse, the last node is at index -1, the second last node is at index -2, and so on. Now for an example. Given the linked list 1, 2, 3, 4, 5, and n equals 2, we get 1, 2, 3, 5. Before we get into the solutions, let's look at some of the boilerplate code I've provided. Here we have a linked list node class. A linked list node can access its value, as well as the next node in the list. This REPR function here lets us print the linked list in a human-readable way. createLinkedList is a helper function to easily convert an array to a linked list, and I've used this function in my test case below. Let's come up with some more test cases, keeping edge cases in mind. One case could be having a linked list of linked 1 and removing that node. We expect to get the empty linked list afterwards. Another case could be starting with an empty linked list, and again we expect to get an empty list back. And another case could be where n is out of bounds of the linked list. Let's say that when n is out of bounds, we'll just return the linked list as is, without any nodes removed. There's a few ways to approach this problem, and I'll go over 2 of them. The first approach is to turn the problem into a remove the nth node from the beginning of the list problem. The nth node from the end of the list is the length minus nth node from the beginning of the list. We can break this up with 2 helper functions. One will take a pass through the list and get the length of the list. The other will take a pass through the list and remove the length minus nth node of the list. Let's start by writing the helper functions. Finding the length is not too difficult. We initialize a length counter to 0 and a temp pointer to traverse the list. We'll traverse the linked list until we reach the end, incrementing our length counter at each iteration. Finally, we'll return the length. Now let's write the remove nth function. It'll be easier and cleaner to write this recursively, since linked lists are a recursive data structure. Here's how it'll work. We'll start with our linked list and the nth node we want to remove. If we don't want to remove the 0th node of the list, we'll keep the 0th node and set the remainder of the list to the value of the recursive call with the remainder of the list now removing the n-1th node. Let's start with the base cases. If head is none, we'll return none. If we need to remove the 0th node, we'll return head.next. Otherwise, we set head.next to the recursive call of this function with head.next and n-1. Finally, we return head. We use both of these functions in our main function, and then we're done. Let's check the test cases we came up with earlier. And it matches what we expect. This solution runs in O of n time, where n is the length of the linked list. We traverse the linked list twice and perform constant time operations at each iteration. The previous approach traversed the list twice with 1 pointer. A new approach uses two pointers and traverses the list simultaneously. We increment the leading pointer n times, then we start incrementing both pointers. Once the leading pointer hits the end of the list, before we increment the trailing pointer, we know that the node following the trailing pointer should be the one that's removed, since we maintain a distance of n between the two pointers. Let's code this approach. First, we'll check for the edge case of n is less than 1 and return head if it is. Now let's initialize our leading and trailing pointers to the head. We'll increment our leading pointer n times. If at any time during this process leading is none, that means n is out of bounds, and we can just return head. If leading is none after this process, we remove the first node, returning head.next. Now we'll increment both pointers until leading is none. When leading becomes none, before we increment trailing, we know we want to remove trailing.next from the linked list. We do this by setting trailing.next to trailing.next.next. Then we return head. If leading is not none, we continue incrementing trailing. We should never leave this while loop without returning, but in case something goes wrong, let's add a return head at the end of the function for safe measure. Let's verify this approach with our test cases. And it matches what we expect. This approach also runs in O(n) time with one traversal through the linked list. If you thought the video was helpful, please like the video. I'll be uploading these every week on Sundays. Subscribe to get notified. Thanks for watching.